SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 22. The last module we were talking about some probability theory, and we were trying to discuss how acceptance sampling can be linked up with the theory of probability, etc. And we looked into the aspect of, if supposing there are two pieces and we are inspecting them, what are the chances that one of them will be defective provided the overall percentage defective is about 8% or so. So we tried to investigate all that. Today we will be talking a little differently. We will actually talk about mutually exclusive events. So if two events A and B occur on a particular experiment or a trial, and further the occurrence of either one prevents the occurrence of the other, then the events A and B are called mutually exclusive. For example, let us say we were talking about the percentage defectives and we were talking about a defective piece. So in two draws, either there can be 0 defective or 1 or 2. Let us consider the one defective case. So if there is a one defective case which is there in such a situation, then obviously out of the two draws that you are making on this whole lot, if one is defective, the other has to be good. Okay, so therefore they are mutually exclusive sets, and one of them would be definitely defective and another would be good, depending on if the first draw is good, the other one should be defective or vice versa. So these are all so called mutually exclusive in nature, and if there is a defective which has occurred, obviously you are left with only a good occurrence. You cannot have a defective occurrence because that will have the number of defectives to be 2. Okay. So for two such events, P, the probability of A plus probability of B is actually the total probability of A or B mutually exclusive events. We have seen this in the earlier example. For example, if 0.08 or about 8% is really the amount of the percentage defective of the population. So in one draw what we were doing is either one defective which would be 0.08 times of one good, which is 0.92, that is 0.736, and the other one, if the first one is a good, then the other one should be a defective, mutually exclusive again. That is how you obtain this. Okay. So this is a very good example of mutually exclusive events. Further, if two events A and A complementary is certain to occur on a trial but cannot simultaneously occur, then A and A complementary are known as the A complementary events. For any such pair of those events, supposing if there is a trial in which, let us say, the event A has occurred and you already know that the event that A should not occur, that means the other events which are apart from A should occur, they are characterized by this A dash here. So the probability of A and probability of A dash combined together is most certain that either A should occur or other events which are there apart from A should occur. So the total probability is 1 in that case. Okay. So therefore the way that A should occur is really 1 minus the probability of the complementary A, that is A should not occur in that particular case. So we have seen in this example a single draw where P dash was given to be 0.08. So if it is a one defective in one draw case is 0.08. Now if it is one good in one draw case, then it should be 1 minus 1 defective in one draw case, that is 0.92. Okay. So the good chances of 92% are exactly complementary to the defective chances of 8% in the particular acceptance sampling. So that is how you classify. Some more laws of probability. So two events A and B are independent if the occurrence or non-occurrence of A does not affect the probability of B occurring. So in that event, again, let us say if you talk about some examples, whenever a process produces defectives independently or at random, so that the probability of a defective on the next piece does not depend on what the preceding pieces were like, then we have a case of independent events. Okay. Such a process is said to be in control, that is stable, even though some non-conformity is produced. Let us look at, so such a process really is said to be in control. Unfortunately, all processes are not in control. For example, let us talk about a different situation where, let us say, we are producing some piston rings, in an assembly line, and there are about close to 3000 parts of piston rings which are being produced. So it may so happen that because of a certain fault which is there in the system, the fault could be, say, let us say, related to stacks of mold at a situation when the iron is not hot enough, etc., and this was realized much later down the production, when the production had already started. So there may be bunching of defects. Okay. So the first 100 may be defective to an extent of 25%, that let us say around 25 defectives came in the first 100, and then afterwards when the process goes on, the remaining 2900 has only 4 defectives. Okay. So therefore there is some kind of an exclusivity and independence of these two events to happen between the first lot and the second lot, and it is really a chance cause that the process was detected at a certain point of time to be defective, and then countermeasures taken because of which defects reduced. So such kind of events then will have to be tackled independently, or it has to be tackled probabilistically in an independent manner, and whenever there is a set of events A and B which are independent of each other, this coming of 25 defectives out of 100, or let us say 4 out of 2900, they are completely independent of each other, okay, and the reasons are therein are completely different of each other. So therefore both A and B occurring should be actually the product of the probability of A and the probability of B. Let us now talk about a second example of probability when we talk about the dependence and equal likelihood. Let us consider drawing without replacement from a lot of n equal to 6 speedometers, out of which 1 is defective. Now n is the number of pieces in one lot. In this case the lot is of size n equal to 6, and the number of defectives in lot is 1 in this case. So 1/6 should be the probability, right. So we consider very simple case which we just draw a random sample of 1 from a lot of 6. So random means that each of the 6 meters is equally likely to be chosen from the sample, and the probability of each is about 1/6. So there are two kinds of speedometers, one is a good one is a defective one, and in such a lot where there are 6 pieces and 1 is defective, obviously 1/6 is the percentage defective and 5/6 exactly is the percentage to be good speedometers. Okay. So now you consider drawing a sample of 2 from this lot of 6. So you want to draw 2, and the overall lot size is 6, and you have only 1/5 or 1/6 of the lot completely defective, and 5/6 is actually completely okay. So what would be the probability of getting a defective, let us say, or a good, let us say, in this particular draw. So out of the 2 draws that you are making out of that 6 lot, one of them could be defective, similarly one of them could be good, or both of them could be defective, or both of them could be good. Okay. Both of them could be defective is not a case here, because there is only one such defective in the lot, so you have to eliminate that, and you are left with only either both good or one defective, one good. So this is a case of 2 consecutive drawings which are not independent. So take the first case of the sample yielding no defectives, that is 2 good meters. So obviously the probability of 2 goods is basically the good at the first draw and good at the second draw. Assuming there are 5 such good pieces in the sample, the first draw the exact probability is 5/6, the second one is 4/5 because you have already drawn 1. So the number of goods have reduced to 4, and out of which you are drawing again, and you should get exactly one of them. So that is 5/6 into 4/5, which is actually 2/3. Okay. That is the probability of 2 good. And if you wanted to do it for let us say the defective, so you should either have 1/6 into 5/5, because one of the draws have already been executed. If you had a bad or defective draw in the first sample, alternately we could also have 5/6 times of 1/5, both of them would typically, so this is good at the first draw, bad at the second draw, so this would all result in 1/6, which is same as having a probability of 1 defective. Okay, so that is how you basically do the you can say dependent events. Given one condition you are doing the second, given that you have drawn one good you are doing another one, trying to draw another one. So there has to be some dependence between earlier and later. So these are completely different than the independent in the earlier slide. So we can also count samples using these permutations and combinations, and this is just a review of what probably you have earlier knowledge about. but we want to see it in case of acceptance sampling, which will just about come in a few slides. So in combinations we consider the example, for example that we have about n objects which we can distinguish between clearly, and how many distinct samples each of one can we draw from a lot of a big size n equal to capital N equal to 10. Obviously the answer is 10, so because you are drawing 10 different samples, they are all distinctly defined, they are different from each other, so you can draw 10 different samples obviously. So we call this a combination of n objects taken one at a time, and symbolization we write it at Cn1, and the Cn1 typically means n factorial by 1 factorial n minus 1 factorial, and this results in n basically. Okay. So n here was 10 for example, and you said exactly 10 draws are possible because they are mutually exclusive and they are completely distinct objects, they are completely different objects with respect to each other. So next consider samples of 2 from say 4 good pieces G1, G2, G3 and G4. Now the number of distinct unordered samples may be found from the number of distinct ordered samples. For example, for the ordered samples you can either have G1, G2 or G2, G1. Okay, so these are essentially the same, only thing is in the first draw in one case you are having G1, in another case you are having G2. Similarly G1, G3, G3, G1, G1, G4, G4, G1, G2, G3, G3, G2, similarly G2, G4, G4, G2 and G3, G4, G4, G3. So you do not have a precedence of what comes first in this particular case, and you are basically arranging all the samples in a certain order or in a certain arrangement. Okay. So but then essentially when you are drawing and you talk about unordered samples, you are essentially meaning the same when you are drawing G2, G4 and G4, G2. That means in one case you are drawing G4 but it is ahead of G2, in another case G4 comes later. So if that order does not matter to us in the case of selection, then we represent it in a little bit different manner, and you can see here that if you are talking about just the representation of all these ordered samples, there are essentially 12 such samples which are there, but if you are talking about the unordered samples, there are only 6 such samples which are there, okay, because you are repeating it just by changing the sequence of what comes first and what comes next. So in one case, that is the ordered sample, and you are drawing 2 out of a lot size of 4, so C42 would typically correspond to factorial 4 by 2 factorial 2 factorial, and that, so this is 4 into 3 by 2 which is actually equal to 6. Okay. So this C42 then therefore represents the unordered samples, and the order is not important in those samples, and the similar kind of a thing can be expressed through permutations. So if we talk about permutation of 4 out of 2, we are talking about the ordered samples where we talk about just 12, which is actually these many sets which have been created in the process of the draw. So now let us consider a lot of 10 distinct pieces, a number of possible ordered samples each of 2 is 10 into 9, that is 90, because there are 10 choices for the first piece, and having made a choice it remains nice choice for the second piece, obviously you get 10 into 9. So 90 ordered samples are there, and exactly half this number is when you are having unordered, that means the sequence is not important in which you are selecting, that times you are having exactly 45 in this, and this you can represent one through permutation. So the ordered samples are always expressed through permutations, and the unordered samples are always expressed through combinations. You already probably know this from your basic class 12th knowledge about how a permutation can be n factorial by n factorial minus 1, and a combination can be n factorial divided by 1 factorial and minus 1 factorial. So having said that, this is a step towards counting of samples, particularly when you talk about acceptance sampling, and already I think I have described this. P and R is n factorial by n minus R factorial. You can represent factorial either in this manner or in the manner that was shown before, and obviously combination would be then n factorial by R factorial by n minus R factorial. And so from this is very clear that how you have calculated the different ordered and unordered samples, as I told in the last slide or discussed in the last slide. So when we talk about inspecting or testing n pieces or n samples, we may search for defects or non-conformances in the n pieces and record the total number of such defects. This is measuring quality by a count of defects. In inspecting or testing of n pieces, we may consider each of the n pieces which may not contain any defects, so they are all good pieces, or maybe the pieces which are actually defective. So each piece having one or more defects is called a defective. Okay. The measure of the count of such pieces are known as the count of the defectives. Okay. So we will consistently use the following symbols here, probably, and also in later discussions. Then n is the number of units in a sample, d is the number of defective units in a sample of n units. So basically d by n is the fraction defective, and then you can represent that by the term q, p, which is the sample of fraction defectives or proportion of the defectives in the sample, and then you also represent q equals 1 minus p, that is the sample fraction good. So if there are exactly d defectives, obviously n minus d are the good ones, and so n minus d as a percentage of n is basically the q value, which is the sample fraction good. And when you talk about the number of defective units, you are basically multiplying just n by n times of p to obtain the number of defective units. So basically you have defined the acceptance percentage in a manner that if you have an idea of the initial sample size from which you are actually drawing, a lot size from which you are actually drawing, just multiplying the fraction defective with respect to that lot size would give you the number of defectives exactly, and similarly number of goods also. Okay. So suppose we had a process with population which had a fraction defective of 10%, that means out of 100 10 are defective, and for a sample size of 4 there could be either 0 defective or 1 defective or 2 or 3 or even 4 defectives which can exist. We can simply represent this process by looking at the various probabilities. Let us say for 4 good pieces or 0 defective pieces you have exactly 0.9, so therefore 90% of the goods are completely defect free, so 0.9 to the power of 4, that is 6561. About 2/3 of the time we draw a sample of n equal to 4 pieces from the process, all 4 will be good ones. Now next we seek p 3 good defectives, 3 good and 1 defective. So this could either be the first one good, second one good, third one good, and the fourth draw defective, or the first one, second one both good, and then the third draw defective and the fourth one good. Again first one good, second one defective, and third and fourth both good pieces, so on and so forth. And so we can actually multiply the probabilities because they are all sort of independent of each other. If the draws are not consecutive in nature, it can happen, any draw can happen at any time. Okay. And so it results in 0.2916 or 29.16% probability of having 3 goods and 1 defectives. You could do the same for d equal to 2 and d equal to 3 and finally d equal to 4, and these probabilities come out to be 4.86%, 0.3%, 0.36% and 0.01% respectively. So we will kind of round off this particular module, and in the next module we will see how using combinations we could arrive at the same probability, just in a way I have shown the earlier example. And after all these examples we will try to look at the distribution that is being made, and can we relate the combinatorial with the distribution so that we can bring out an overall way of representing the acceptance sampling methods in terms of fraction good and fraction defectives, so that at one go you can do the calculation straight away and find out what is the overall probability in that particular case or situation. So having said this, we will close this module, and then in the next module we will just wait on, or we will discuss the remaining portion. Thank you.